Alright, let's go and get started. Thanks guys for coming out so early. We know it's early, but with this weekend and stuff, it's just the best time to work our schedules. So there's a class that comes in here at 8, so we're gonna be a little bit shorter than our normal review, so we're just gonna have to keep it crisp and keep it moving. We'd love to answer all your questions, but we won't be able to stay after this time and answer all the other questions you have. So let's just jump right into it. The first thing I want to talk about today is balancing redox reactions. There's two ways that you've seen it done. Dr. Macedoni did an example in class of an acidic reaction, and then for your smart work problems, they were mostly basic. And we found that people had a little bit of a tougher time doing it under basic conditions. And so that's what I'm going to do today. I'm going to walk you through the process, the way that I learned. I know a lot of other TAs have taught it differently, and there's many, many ways you can balance a redox reaction. So if you have a way that you've been doing it and you feel comfortable about it, by all means, just keep going with it. You don't have to switch to the way that we do it, but I'm just going to teach you the way that I learned it and that I'm most comfortable with. So what's the first thing we do in balancing a redox reaction? Half reactions. So in this reaction right here, we have SO3 2 minus going to SO4 2 minus, and my other one would be MnO4 minus to Mn2 plus. The next thing I want to figure out is what's being oxidized here and what's being reduced. Who can tell me? Yes.
Manganese is being reduced and sulfur is being oxidized.
Okay, that's good. I'm going to walk you through the process of how you figure that out. So a couple rules you should always remember. Oxygen will always have an oxidation state of -2. So whenever you have oxygen in one of your compounds, the easiest thing to do is just start counting that. So let's just do SO3 as an example. For each oxygen, it's a -2, right? And I have 3 of them. So that's a net total of -6. But my total charge on this whole compound is -2. So I have a -6, and I know I have to end up -2. So sulfur would have to be +4. Okay? So sulfur is +4, and let's look at it in this case. Each oxygen's -2, so I would have a -8 coming from my oxygens. I have to be -2 total, so sulfur would be +6 over here. So if it increases in charge, then it's oxidized. We lost electrons there. And you'll see here that manganese was reduced. So what do I do next? I'm going to erase this for now and I'm going to do each half reaction first. So what I always do next is I balance my oxygens with water, right? So I have 4 oxygens over here, 3 oxygens over here. So the next thing I always do is add a water to the side that needs it. So now my oxygens are balanced. The next thing you do is I balance my hydrogens with H+. So I only have 2 hydrogens on this side and none on this side. So I'm just going to add 2 H+ on this side. Now if we were doing acidic conditions in this case, we could just move right ahead and start balancing our charge. In the case where they say it's basic, you can't have those H+ ions in there because it's going to make an acidic solution. So what we have to do, the way to easily think about it conceptually, is we have to neutralize those. So anytime I add an H+ and I know I'm in basic, I add 2 OH- immediately to that side. And that will neutralize with 2 OH- to just make 2 H2O. But if I add 2 OH- on this side, I have to also add it on this side. So I have 2 OH- here. Now, if you did it all out, you should see all the hydrogens are balanced and all the oxygens are balanced, sulfur is balanced. Everything's good but the charge. So now let's go ahead and balance our charge. And when you're balancing your charge, you have to take into account your coefficient in front. So coming from these 2 OH-, that would be 2 minus charge. Okay? Water's neutral, and this has a 2 minus charge. So I have a total of 4 minus on this side. Over here, I have a 2 minus and a neutral. So where do I have to add electrons? Yeah, I have to add electrons over here. I have to add 2 of them. And now that half reaction should be good. Yeah.
So with the
original equation, do you have to take into account the coefficients in your
In your balancing?
balancing?
Yeah. Mm-hmm.
What about in the half reactions?
Yeah, I would always make sure it's balanced with coefficients.
Okay.
Yep. All right, so that should be good. And what I would do if you're in your exam, I would always self-check. So if you feel like you did it right, go through and actually count it all out. Check your charge, check all the different elements, and make sure they're all balanced, just to make sure you're safe. Because these balancing redox reactions, it's very, very systematic, and so you guys really shouldn't miss this on the exam. Once you understand how to do it, it's very systematic. You just do it all out, and it just works. So these should almost be gimme points on the exam. Okay, let's do our second half reaction. We have MnO4 to Mn2+. So the first thing I need to do is balance my oxygens. I do that with water. So I have 4 oxygens over here, none over here, so I'm going to put 4 H2O over here. Next step, I'm going to balance my hydrogens with H+. I've got 8 there, so I'm going to add 8 H+ right here. And remember, we're in basic conditions, so I'm going to add 8 OH- immediately. And those are going to cancel to make 8 H2O. And if I add 8 OH- on that side, I have to do it the same over here. Right? Now all that's left is balancing the charge. So I have 1 minus on this side, and over here I've got 8 minus plus 2 would be 6. So where do I have to add electrons? And how many? 5 electrons on this side, right? Now, once you have both your half reactions balanced, the next step is just to simply get it so the electrons can cancel. So we're going to multiply these entire equations by something to make sure our electrons cancel. So I have 2 over here and 5 over there, so the easiest thing to do is multiply this one by 2 and the other one by 5. So I'm going to multiply this whole reaction by 2 if you guys can visualize that. So I get 10 electrons, 16 waters, 2, 2, 8, and 16. Now this one I'm going to multiply by 5 to get it to get my electrons to cancel. So I'd get 10, 10, 5, 5, 5, 10. Alright, so electrons are going to cancel. And now what we can do is just start combining things. So over here, I have 10 OH minus, and I have 16 over here. So what I can do is I can just say, okay, I'm going to cancel all those 10 out, and I'm just going to leave 6 over here. Those 10 just canceled each other. Now over here, I have 5 waters and 16 waters. That's 21 waters. Over here, I have 18. So I can erase all 18 over here and just make these 3. I have 3 left over. Now we should be good. So now it's just adding them all up. So it should be 5 SO3 2 minus plus 2 MnO4. I'm not writing the phase right here either, but just make sure in your exam that you write the phase of each. Plus 3 H2O, and that should give us 5 SO4 2 minus plus 2 Mn2 plus 6 OH minus. Okay? And if you're in your exam again, double check yourself, go through it, count the charges, count all the elements to make sure they're all good. Any questions on this, balancing redox? Alright. So now let's go on and talk a little bit conceptually about cells and how they work. I feel like to really do well in this exam, you have to understand cells, the different types of cells and how they work. So first cell, probably the most simple, voltaic cell. Who can explain to me how a voltaic cell works? It's early. Yeah.
You guys like the top one?
Yeah, the top one.
The electrons are gonna flow from, they're gonna come off your zinc solid, go across to your copper. Actually, no, it's not. Is that right?
Mm-hmm. Yeah.
Yeah. And then they're gonna attach to the copper ions that are in solution. That's gonna deposit on your copper solid.
Mm-hmm. Yep. Go ahead.
And when it does that, that creates the charge that we need to power things.
Yeah. So the first thing with the voltaic cell, we have two different metals, and you guys have been working with those reduction potential charts. Now different metals have different potentials to be reduced. And so when we have a voltaic cell, the one that's going to be reduced is the one that's going to have the most positive reduction potential. So in this case, it's copper. I didn't give you the reduction potentials, but on the exam he would give it to you. And so you could see, okay, copper is going to be reduced here. So if copper is reduced, it's going to gain electrons. So if copper is reduced, I know zinc is oxidized. And how this works conceptually is because of these natural reduction potentials, we can get electrons to flow. Because zinc is really likely to get oxidized and copper is really likely to get reduced. So what happens here is we have a zinc solid, and since it's oxidized, we're shooting off zinc 2+ ions into our solution. And when we shoot off those 2+ ions, we basically have excess electrons now in our metal. And so what they're going to do is they're going to flow through the wire onto this copper metal. And once we have extra electrons on our copper metal, copper is really likely to be reduced. So these copper ions in solution are going to come to positive. You can think of these 2+ ions as really wanting electrons. And so when we have electrons here on our metal, they're going to want to come and grab onto those and stick onto the metal. So in our oxidized, we're shooting ions into solution. On our reduction side, or our cathode, the ions are coming to stick onto our metal. And that's basically the gist of what you have to know about voltaic cells. Now, electrolytic cells are basically the same thing, except what you do is you run a current through it to push it the opposite way. Yeah.
And can you remind me what the salt bridge does again? Because I know it lets the ions flow. Is it letting the ions flow so that...
Yeah. So you can think of our solution, we need to keep it neutral, right? And so if we're shooting off positively charged ions in here, you can think of the salt bridge as doing neutralizing those. So as we shoot off these zinc ions into this solution, our nitrate ions are coming in to neutralize those. They're basically just complexing with the ions. And in this case, we're losing positively charged ions. And there would be an anion in both of these as well. And so if we're losing positively charged, our cations, then cation is going to flow in. So it basically just helps keep balance. Yeah?
So would it be safe to say that if the salt bridge wasn't there, the electron flow between the two electrodes would be decreased because the ions and the excess ions in the solution would be hogging the electrons or attracting them?
Yeah, because if we built up a big enough concentration gradient of these zinc ions, they would no longer be oxidized because we already have too many of them in solution. So the salt bridge is able to neutralize them so they can keep pumping off and get oxidized. Yeah. Yeah.
It shows that it's 1.1 volts. For electrolytic cells, does that have to be overcome to go backwards, or is there anything like that?
Yeah. Mm-hmm. So I just made up that number, the 1.1
Yeah.
volts. I'm just showing you here. I remember on one of our exams, we had to draw an electrolytic cell, or a voltaic cell. And so the voltometer is just one of those things to include. So that's why I put it up there, just so if you get it in your notes and you're studying it later on, that you remember to put the voltometer there. But the voltometer is basically just telling us, the electron flow, how many volts we're getting out of that.
So this picture is for next test for written.
I remember having to draw a cell, and so I don't know if you guys will, but that's just that's what we had to do when I took the class. So I thought I'd draw it up there just so you guys make sure you understand conceptually. It's on the necessary skills as well. You understand how it works. Okay, so moving on, let's talk about concentration cells. I feel like concentration cells are a little bit more complicated than voltaic cells. So, in the concentration cell, what I'm telling you here is that we have the same exact metal and the same ions in our solution. The only thing that's different is we change the concentration of each ion. So I'm telling you here that our Pb ions in here is 0.002 molar, over here it's 2.5 molar. So which way are the electrons going to flow? Yeah.
So I'm guessing that the ones to the left is the anode, and so it's the electrons are gonna flow to the right.
Think about it again.
Okay.
I drew it opposite this time because you guys get really familiar with anode on the left, cathode on the right. It doesn't always have to be that way. So, conceptually, we have a slower concentration of ions in this solution than here, right? And so what these want to do, I can say I have this much concentration of lead here and this much here. What these want to do is they want to come out and be equal to each other. So this is actually going to be my anode because this side wants to increase its Pb2 plus ion concentration, where this is deficient and this has excess. So naturally these ions are going to, this metal over here is going to be oxidized. I'm going to be shooting Pb2 plus ions here. My electrons are going to be flowing this way onto the cathode. And then with excess electrons here, my cations are able to deposit. And when these are depositing, I'm decreasing my concentration on this side. And when these are shooting out, I'm increasing the concentration. So what you'll see is these will actually come out and you'll reach an equilibrium. When the equilibrium is reached, you will no longer have electron flow.
So will the one with the lowest concentration always be the anode?
Yes. Yes. Yeah.
So, this, I thought it was the other way around, so it's going to be weird for me. But so it flows, the electrons flow from the lower concentration to the higher concentration.
Mm-hmm. Yep. Because what I'm telling you here is that the concentration of lead ions, that's what we're looking at. We're not necessarily looking at where we're deficient in electrons. It's our concentration of lead 2 plus ions. So if I have less in solution here, then this metal is going to want to make more. So I shoot more lead ions into this solution, and then my electrons, when these get oxidized, my electrons have to go somewhere, and then they travel through this wire, and they end up here. And you can think of my solution here as really concentrated of lead 2 plus ions, and so I want to get rid of them. So with these extra electrons on the cathode, these are going to start depositing onto the metal. And so my concentration of lead 2 plus ions here is going to decrease, where on this side, on the anode, it's going to increase. Any more questions on these cells? Okay, let's move on.
The concentration cells only have one metal in it, not two.
Yeah, they're the same metal, just different concentrations. Okay. Here's another thing you guys have been working on in your smart work. I'm just going to give you a minute to start this problem. What I want you to do is, let me make sure the video can get it. What I want you to do is calculate the delta G for this reaction. And I gave you the reduction potentials right here. The AL is negative 1.676, Br2 is 1.065 volts. Okay?
Do I just put the necklace on the other thing there?
Yeah. Could you read those two values one more time?
Okay, the AL is negative 1.676 and Br2 is positive 1.065. What's our N here?
6.
6. If you're confused on how to solve for N, what I would do is write out the two half reactions and then balance them with electrons. I wrote one of them here. For the sake of time, I'm not going to write the other one. But you can see here that we have a positive 6 charge on this side, neutral on this side, so I have to add 6 electrons over here. And if you did the other one out, you'd see that there would also be 6 electrons transferred. Okay, let's get started. So, first thing I need to do when I'm doing this equation, when I read this problem, is understand what equation am I going to use. Anytime we relate delta G to voltaic cells, we're going to use this equation right here. Delta G equals negative NFE. So the first thing I want to do is solve for the E naught of the cell. So I come over here to my reduction potentials, and which one of these is going to be my reductant? BR is, right? The more positive one is going to be what's reduced. So it's always the E cell, the E naught equals cathode minus anode. So it would be 1.065 minus a negative 1.676. And when you do that, you should get 2.741 volts. And so now what we can do is just, we have enough right here, we just plug it all back into our equation and solve for delta G. So delta G equals negative 6, my N is 6, there's 6 electrons transferred here. Faraday's constant, 96485, times my E naught, 2.741. And when you do that, delta G should equal negative 1586 kilojoules. So this is pretty straightforward. I think the number one thing is to first understand what equation you're going to use. Second, solve for the E naught, and then just plug it all in. Anyone have questions on this? Okay. I've just got one more example, and then we're going to go to break. Okay. So next one, calculating E cell at non-standard conditions. When I say that, who knows, what equation am I going to use? The Nernst equation. Okay? Alright, so I'm going to give you guys another minute to solve for this. And this is actually, it's the E naught minus that. Who knows how to interpret this type of notation for a reaction? Okay, let's go over it, because I don't want you guys to see something like this on your exam and have no clue what's going on. So what the single lines are phase barriers. Double line is where your salt bridge is. So on this side, I would have zinc and zinc plus, salt bridge. So basically, there's two containers right here. And then I have copper metal with copper ions. And from these reduction potentials, you can figure out which one is the cathode, which one's the anode. Okay, for the sake of time, I'm just going to go ahead and get started on solving this. You guys can go back and watch the video later and just, pause the video and then try solving it on your own. But we're a little bit shorter on time today, so I just want to get started. So, first thing we can do is calculate our E naught. It's cathode minus anode. When you do that, you should get E naught equals 0.78. It would be 0.34 minus negative 0.44. Then we can plug this into our Nernst equation. For E naught, we have 0.78. What's our numbers of electrons transferred here? 2. And what do we do for log Q? What's our Q? Yeah, so products over reactants. If it's hard for you to see it in this case, what I would do is write out the entire reaction. if you wrote out the entire reaction, it would be zinc plus copper 2 plus equals zinc 2 plus plus copper solid. So we know that our zinc concentration is what's on top here. That's our product. So we have 0.15 over 0.35. And then you just do it out in your calculator, and when you do it, you should get E equals 0.79 volts.
How do you know the equation starts with zinc and not with copper?
So I wrote it in kind of goofy notation just because I wanted to teach you guys this. But what you would have to do is look at these reduction potentials and see which one's going to be reduced and which one's going to be oxidized. So if I know here that copper is going to be reduced, zinc is going to be oxidized. So I'm going to start with zinc metal, and copper is going to be oxidized, so I'm going to do that, and that's going to make zinc 2 plus and copper solid. So then our solids never matter in our equation, so it's just the concentration of zinc 2 plus over the concentration of copper 2 plus. Yeah?
Is it always, in the line notation, is it always anode and then cathode? Like reading left to right?
I'm not sure. Do you know that, Braden?
I think it is.
I think it is, yeah. But yeah, I would just definitely understand how to interpret this type of notation. Okay? Are we good here? Okay, I'm gonna give it to Braden.
Yeah. All right, guys. Let's talk also about this a little bit, but with this problem right here. So you should be able to do this really quickly. Looking at this equation, with those reduction potentials out of the book, what is the E naught of the cell? This is, we just did a couple problems like that, but this one I want you to do really quickly. Okay? Grab your calculators, everybody do it really quickly.
Does it say 0.779?
Yeah. 0.779 and negative 0.4676. Who has an answer?
1.25.
1.25. Who else has an answer? What else? Did anybody get anything different? So the answer to this problem is negative 1.25. Right around there. So the problem with this is oftentimes we'll jump straight to cathode minus anode without looking at actually what is the cathode or what is the anode. What is being reduced and what is being oxidized. In this case, my reduction potentials would tell me that my silver here is most likely to be reduced, right? It's got a higher potential. It's more easily, it takes those electrons better. But the way that I wrote my reaction and how I'm trying to do it is actually opposite from that, right? So make sure that you don't get in robot mode and are just always just looking at the potentials and doing cathode minus anode, but rather make sure it's verified in the equation and you actually are oxidizing something and reducing something and you're putting it in there into that equation correctly, okay? So just look at that.
Does that tell us that this is an electrolytic cell?
To tell you that it's an electrolytic cell? Not necessarily, but most likely. Yeah, not necessarily, but most likely. Yeah. Okay, so now let's look at this question, kind of going with oxidizing and reducing. So we talk about that, and I think you guys understand that pretty well. What does it mean to be oxidized, right? I'm losing those electrons. But what does it mean to be reduced? I'm gaining those electrons. And oftentimes in these cells, like Corbin drew really good depictions of those, what's happening really in nature is one of those metals really can take those electrons. And in a metal, right, because of the structure of a metal, the structure of a solid, we get what we call oftentimes a sea of electrons. These electrons will just sort of flow around. Now, we don't have an unlimited supply of those, right? As soon as I start taking some of those electrons off of one metal, I'm going to be producing positive things, right? Because I'm losing all my negative charges. So that's where those cations come from, right? And whether or not I'm losing electrons or gaining them tells me if I'm oxidized or reduced. So going along with that, not only are there things that are oxidized and reduced, but there are reducing agents and oxidizing agents. So those are always the things that help me to oxidize something or help me reduce something. So in this case, really quickly, what is the best oxidizing agent of these three? What do you guys think? So you're saying this is the best oxidizing agent, okay? I say it's this, right here, and not SN4+. and I say that because if I want something to be my oxidizing agent, it's helping something oxidize, so it's being reduced. So I want my thing that reduces the best, right? So I look at these potentials and I say, okay, this is my oxidizing agent, right? Another trap to not fall in when I'm doing these problems is if it asks me to circle or square my oxidizing agent or something like that, it's not just the Fe3+. For instance, if Fe3+ in the equation I wrote, let's say I wrote it that it was being reduced, but the equation showed it on the left hand like this, something like that. So I didn't actually see a charge, but when I assigned oxidation states, kind of like something Corbin was talking about, I noticed, okay, yeah, this was reduced. It went from a 3+ to iron solid. When they say circle the oxidizing agent, it's the whole thing, right? I wouldn't just circle just this piece, but circle the whole molecule and don't fall in that trap. Because that whole molecule is what's helping me oxidize, right? So, yeah, that's good. So that's just a little summary again of some of the things Corbin went over. Now, what I wanted to talk about, what my next couple minutes will be about, are these problems that we've been going over where we're kind of doing dimensional analysis, but not exactly, right? It's not the dimensional analysis that you guys are so used to, where it's super, numerator, denominator, but it gets a little bit messy, and there are several ways to do this, and I want to just give you my way and give you the way I think is easiest, because these problems are not always one line. Sometimes we have to solve a little equation and then plug it into our dimensional analysis, and that seems to be like the easiest way to understand I know what I'm doing, right? Oftentimes, whenever we're given these problems where we're given amps or volts or anything like that, watt hours, right? And they want to know, this is the way a battery is working, they want to know how much of something is electroplated. We're going to go from volt and watts, these abstract units that we're not so used to dealing with in chemistry, right? And now we're trying to get to mass and moles, which we are used to dealing with. The middleman to get from those two is coulombs, right? And Faraday's constant. So anytime you read a question that says, okay, we have a battery that does this, how much is electroplated or how much mass of something, know that you need to somehow get to coulombs, use Faraday's constant to make the bridge from coulombs to electrons, to moles, to mass, right? So if you can get to coulombs and coulombs alone, then that makes that jump, right? Now, not all problems want you to get to the mass of something, but I think this one that I wrote, yes, this one does. So before we solve this problem, there are a couple equations that I want to write up on the board, and hopefully you guys can really internalize these and start using these to solve these problems, okay? The first one says that an amp, right, an amp is equal to a watt or power divided by volts. Now this is important, right? An amp is my current. That's like if I stood at the bank of a river and I'm watching the river flow by, my amps is the current or the flow. I stand there in one spot, how much flows by, right? So my amperage right here is how many coulombs flow by in a second. And a coulomb is a charge, right? So basically, in a wire, if I stood there, I want to know how many coulombs are passing, how much charge flows, and at what rate, right? So I can get amps from taking watts and dividing it by volts, and that will give me amps. Now the unit for amps is also coulombs per second. So an amp is also equal to a coulomb per second, right? This flow, okay? So that's important to understand. Amp is equal to that. A volt is equal to a joule per coulomb, right? And a watt is equal to a joule per second. So we'll notice here we have all of these units here, right, to this one equation, and each one of these breaks up into its own little units, so it's hard to do this dimensional analysis really crisp. So instead of giving you time to solve this, we're gonna jump right into solving it, okay? And then you can look this through on the video so that we have enough time to do this. So suppose the current from a battery is used to electroplate an object with gold, right? Calculate the mass of the gold that would be deposited by a battery that delivers 1.65 amp hours. So this is one of those questions where I'm talking about a battery that gives me 1.65 amp hours, this abstract thing, right, that I'm not used to dealing with, and I'm trying to get to a mass amount of gold that's deposited. So the first thing I want to start with is, okay, this is the only thing I know. I'm going to start with this, and I'm going to try to get myself to what? Coulombs, right? I want to get myself to coulombs, because coulombs is my middleman to get to mass. So I'm going to start with 1.65 amp hours. 1.65 amp times hour here. So it's going to be hard to start the dimensional analysis like this because it's like, okay, now I'm trying to put amps down here or hours and I'm not sure how to start. But what helps me is understanding that an amp is really a coulomb per second. So I'm going to change this first piece of the unit to exactly what it still equals, right? This is really saying 1.65 coulombs per second times hour, right? So I'm going to start my dimensional analysis. Let's get rid of hours here. In every 1 hour, there is 3,600 seconds, right? You could have gone to minutes to seconds, and that's fine. And this is good because I realize right now, oh, now my seconds can cancel with my seconds right here as well, right? And my hours cancel with my hours. And if I do that, what am I left with? Coulombs, which is exactly what I want, right? Coulombs is my middleman. So when I do this, I'm left with a number in coulombs. And that number, I think I did this math out, is 5940. I'm left with that many coulombs. So now it's easy. Now the dimensional analysis is more like what I've seen. I put Faraday's constant in. So that says that there's 96485 coulombs for every 1 mole of electrons, right? In this case of my gold, right, I want to know how many moles of electrons are transferred in gold. Well, Au plus, so just 1 mole of electrons, right? So sometimes you have to go to the periodic table, look at when gold is oxidized or reduced, how many electrons are transferred. Just 1 here, so I'm going to say there's 1 mole of electrons transferred for every 1 mole of gold. I'm going to bring my dimensional analysis back over here and say that for every 1 mole of gold, I weigh 196.967 grams. And when I do that, I'll notice every unit will cancel, right? All of these units, coulombs that came to here, canceled there, right? My electrons canceled, my moles canceled here, and I was left with an answer just in grams, right? And the answer to this was 12.126 grams. So I was able to use what I understood about the amp, a coulomb per second, right, to make this dimensional analysis a little bit easier to understand, okay?
Where did you get the 5940?
5940 coulombs if I did this math out. Right here.
Just
Okay, let's do this next problem that is also dealing with these weird, strange units. So let's remember up here what I wrote in these equations and what they mean, right? So this problem says a battery can provide a current of 3.7 amps for 7 hours at 1.6 volts. How much energy in kilojoules is produced by this battery? Okay, so I'm given amps, I'm given volts, I'm given hours. I want to know energy. I want to know joules. So I look at these equations over here. I know amps is a coulomb per second. I know a volt is a joule per coulomb. I know a watt is a joule per second. And I know my main equation says that amps is equal to a watt divided by volts. And I know I have amps and volts. I could solve for watts. A watt is a joule per second. And I know how many seconds I'll have because I'm doing this for 7 hours. So that seems like the best thing to do.
Really quick, I'm sorry, really quick on the last problem. Isn't there 3 moles of electrons being transferred? Is it 3 or is it just 1?
Just 1.
Okay, I got that. That's
Okay,
correct.
just 1 there. Okay, so let's do that. Amps. I know amps is equal to watts divided by volts. How many amps do I have here? 3.7 is equal to watts, which I want to solve for, divided by my volts,